Sergey from Wharton, it is also clearly business school work. So we might work at a slightly different level of abstraction when it comes to the electricity grid as some of you in the audience, but I'll try to sort of point it out. But also one of the things I would love to hear your feedback on the second half of the talk is sort of like, what are some of your concerns around feasibility? Sometimes what you do at the business school, you kind of like, this is a really cool business innovation. Let's sort of try to figure out the economics of it. And then there's what we call the engineering challenge that might still be a challenge of sort of like implementation. And so the talk is actually going to be almost like a reverse order, where I want to start talking a little bit about geospatial flexibility. Then we'll get to moving money around and moving batteries around. And giving the audience, I'll keep the why one should study energy motivation a little bit shorter than usual. We've talked about the duck curve before, but of course, we should do something as a global society about our emissions. And what I think from a sort of business school perspective in particular is really nice that although energy is a huge culprit, together with renewables, we have those new technologies like solar and wind, and I guess solar in particular, that have gotten the cheapest or have become the cheapest forms of energy in expectation. Now, I'm not the only person who has noticed this, right? If you look at solar capacity over the last 2 decades, you've seen a sort of 1,000-fold increase. And you could kind of joke that if you start at zero, increasing 1,000-fold is kind of easy. But just for like the magnitude from 22 to 24, the world has added more solar than the US's generation capacity total. And so I think we're now sort of just at a scale of transition. We're figuring out how do we integrate those renewables becoming more and more paramount. And most of my research is on this. And so here's the promised duck. For the duck curve, I don't need to spend too much time talking about it, right? But in the old days, as little as sort of 10 years ago, you had fairly stable electricity prices throughout the day, maybe a little peak in the evening when demand is highest. And then fast forward, and this explosion of solar capacity gets you this duck curve. And I think many of you in the room are kind of figuring out, okay, how do we deal with this? Of course, negative prices or zero prices during the day is bad if you want to entice more solar development. And here, this sort of peaking at the neck of the duck is a problem and puts our grids under strain. And so I think as many of you in the room, my work is sort of trying to figure out how do we deal with this, but particularly coming from this, what I call sort of decentralization aspect. And so one of the features that I think are really exciting about those technologies is that they're kind of small and modular. And so whether you have those batteries that someone could install in their own home, like in their own house, or there's a Tesla charger here, but we have a project together with BMW where like individuals get EV cars, and then one OEM or like a local developer might install the charging solutions for it. And so what I find really interesting is not only how do we sort of accommodate more renewables in the grid, but how do we coordinate all those different actors in the space. And even though this is like maybe an EV and the residential solution is even more decentral. Oh, yeah, and here's, by the way, the promised 5 trillion a year needed in investments to make this all work. But to me, even the utility scale storage is a decentralization question in the end. Because the technologies, I put a picture here, are still sort of modular. Like the cells themselves are modular, then you put them in packs, and ultimately you build those containers full of battery storage, and beyond a certain scale, as long as you can find land and you have access to someone selling you those batteries, you can become a utility developer. Of course, starkly simplifying, but the main notion here is that individuals with access to batteries and land can connect to the electricity grid and start changing how prices operate at those different nodes. And so we've seen, I think, this rapid increase here, partially because costs have come down of batteries, of course, that makes it more profitable. And then I think one particular salient inflection point was when batteries became cheap enough so you could run them on energy arbitrage alone. Before that, you needed sort of frequency regulation, value stacking, multiple different revenue streams. And now in many markets, you can only do arbitrage, which then means, again, for an individual investor, I don't need a queue. I don't need to compete for some spot in an auxiliary market. I can just go and build my own battery. We can say it's slide 3. We're actually done. We have a growth in batteries. We're all done here, and we'll go over to the food. But I want to point out 2 things that we're going to look at in the paper and then suggest a possible solution to that is problematic about this decentralization. And for that, let me walk you through a little example. Like imagine you're a battery developer and you want to install some battery in Boston. and you could pick your location. So you might say, okay, I'm going to Kendall Square. I kind of know what the local nodal price here is, and what I'm living off of is this kind of spread between low and high. I'm going to buy in the middle of the day. I'm going to sell at night. But that's not the only choice, right? You could go to multiple different locations. You could go downtown. You could go somewhere to Mystic River, and they each going to have their own kind of price. And so one of the challenges with this decentralization approach is that it's not just the battery developers making their moves. It's anyone you could imagine. A solar developer that might come to this node, the AI data center. I had to throw in AI at some point in time. So the AI data center popping up, maybe not in North End, but in general, or like a factory coming right next to you. And so because it's not a centralized planning tool anymore, and you have so many actors impacting this, it is not clear how those sort of prices that you're depending on as a battery developer are going to shake out. And so what we wanted to do, there's a little graphic here. It's a little bit like whack-a-mole, effectively, where whack-a-mole is like the profit you can make, and you want to hope for a really profitable spot. Problem is you're installing physical infrastructure. And so normally in whack-a-mole, right, you have this little hammer and you can like go wherever you want. Here you have to choose one location. This is where you're going to put your bet. You're going to put your battery, and then you hope that the profit and the volatility arises. And to make this even more complicated, you're actually not, and then this is the last bit of the analogy, and we'll move on. You're not just the only person playing whack-a-mole. There's other people with their same hammers also looking for the same kind of profit opportunity. And so what we're going to look at is we're going to look at those two kind of questions. Like what factors drive differences in battery storage profitability, and then how is the impact of sort of competing battery developers joining one node? How large is that impact of them joining on profitability? That's going to be the first part, and then in the end, we're going to look at how could mobile batteries solve some of this. Yes.
Are those numbers based on like energy arbitrage?
Yes, exactly. So the empirical numbers, not just like the fun story that I was telling with the whack-a-mole. If you look at sort of the more mature storage markets, you have actually seen storage decrease, storage revenue decreasing as some of the price spreads have shrunk. Of course, this is volatile, so I'm not promising this is going to continue indefinitely, but it's just one of those indications where if you get a lot of storage, the prices start shrinking.
So the starting point is that the developers are able to anticipate the current level of price fluctuations at one location and more than one location while trying to make investment decisions. Is that what the starting point?
Yeah, excellent question. I think even before that, like the very first point, I'm just going to sort of descriptively show you how much volatility there is in the system, which the developers are working with and sort of trying to anticipate. And then we're going to look at, now that at some point in time you as a developer have to make your bet, how large is the impact of one battery joining an existing node, and what is this going to do to prices then? And then as a third step, after we understand sort of competition and volatility, what could mobile batteries do about it?
And when you're talking about this the fluctuations in the prices, you are going to account for network effects also in the how engineering aspects. So that's what I'm asking.
Yes and no, but I'll show you what we're doing empirically. What we're going to do is we're not going to account, like we're not going to recompute like Kirchhoff laws or something, but we're going to compare two nodes in a particular fashion, one with a battery installation and one on the same transmission line without one. And this is one of the things I want your feedback on is like, is this reasonable? Is this insane? Like, what should we do differently? So I'll show you what we're currently doing, and then I'm hoping to walk out of here with a mildly improved ordinary motion. All right. I'm going to skip the literature review given time, but I know many of you are working in this space. Happy to chat. I'm sort of in the clean energy space. I think flexibility is sort of a key issue that operations people love, matching supply and demand, whether it's in retail sectors or energy. But I wanted to kind of start showing you how before we get into sort of competition and dynamic effects and everything, how we're computing the daily value of storage. Because I know there is a lot of work, including in this group, on sort of like how do I stochastically optimize this? We're going to make our life a little bit simpler to start. And so what we're going to do is imagine you have a 2-hour battery. For most of the talk today, I'm going to sort of assume a 2-hour battery is sort of like the modal duration of storage. And it can have sort of 3 states. It's either fully charged, it's like half charged, or it's empty, half charged, fully charged. And then let's say you start with a fully charged battery. For the next hour, you can sort of do 2 things. You can either do nothing with your battery, in which case you get no payoff, or you can sell electricity back to the grid. If you sell, you get whatever the price is locally, and then your charge is going to be lower. And you can do this kind of every hour of the day. You can buy, sell, or do nothing. And you can write this down as a dynamic program where ultimately you kind of want to know, like, what's the optimal value of storage that I can get on one day in one particular location. And at least from an OR perspective, I think it's kind of neat that you can somewhat think of this as a shortest path problem that you want to traverse from here to here, where basically the edges that you're connecting are the prices. And so this is, of course, taking sort of the price vector as given. And so if you have a day-ahead market, I think this is pretty reasonable because you can lock in all the prices in the day-ahead market. Of course, in the real-time market, you might not perfectly be able to forecast all of those. And so I'm going to show you partially the results for both. And I think the realized profit of an actual battery developer would be in the middle. The main reason why we're doing this is we didn't want to take a stance on like what actual algorithm is a given developer running. But at a high level, what this allows you to do is sort of dynamic program. You get from, I observe a certain set of prices across 24 hours in a day. You could make this more granular if you wanted to, 15 minutes, 5, to I get a value of profit in a location on a given day. Okay.
Just to clarify, so you said it's a 2-hour battery.
Yeah.
Is that why you can also move from the lower to the upper stage?
Yeah.
Entirely?
Yeah, exactly. Like if you had a battery, let's say if it was a 1-hour battery, you could sort of move the entire, like you could discharge in one entire day, and vice versa. If you did like 4 hours, you could kind of play it. It's most of the results I'm going to show you work for 2 hours. I think up until like 4 or 6 would probably be fine. If you want to talk longer duration storage, you probably have to sort of start changing the model up a little bit because there might be other effects than just the daily prices.
These are predictions, these 3 indices, P, D. Why do I need 3 indices in this?
Which one?
The prices, the P.
So the prices are in the day ahead market, they're just known. Like you can lock in, like you look at whatever the price is going to be tomorrow, you can like basically buy the entire sequence of prices, and you can just look at, okay, if this is whatever is on the day ahead market, I know that I might want to like start charging at 8 a.m. in the morning or 10 a.m. and I'm going to sell at like 7 and 8 p.m. Of course, if you're in the real-time market, you could write this down as sort of a learned policy over the same kind of algorithm. And then one thing I neglected to say, like the degradation cost of the battery optimization comes in here as well. So your arbitrage profit is whatever the max of doing nothing, buying and selling. But then we're going to force it for the battery to always be fully charged at the end of the day. Of course, you could sort of relax that. You could say the battery never needs to be fully charged, or it only needs to be fully charged every few days. What this allows you to do is you can sort of break up the problem into divisible chunks of like profit per day and then separate it out. Of course, profit might be higher if you give yourself more flexibility than that.
What is E?
Sorry, this is the efficiency loss. So and you could play around with, like, for example, if you didn't want the degradation or the efficiency to only happen during discharge, then you could play it.
So degradation is a constant, or
Yeah, it's a constant over the capacity. For all the empirics I'm showing you, it's going to be $20 per megawatt hour cycles.
Okay.
But you can play around with it. And I know that degradation may not be a constant depending on like how rapidly or not I discharge the battery. That's why I'm saying I want to be upfront of like how close we were stepping to the engineer. Cool. So what we're going to do initially, just to like get our feet wet a little bit, of quantifying how volatile is the profit really. If I'm a developer, and we're going to look at PJM, the largest wholesale electricity market in the US, covers all those states, and we're going to get the nodal data from 2019 to 2024, and we're going to look at 576 high voltage nodes. Above 69 kilovolts, basically with the idea of we wanted a voltage where it's sort of reasonable that you can connect the utility scale battery to it, so we're not at some distribution level node. And what we did check is that even if you go through all the nodes in PJM, at least one of those nodes in our data set is going to be, I think, more than like 9.98 correlated with something also. So the main hope is that by having only a focus on the high voltage nodes, you get kind of good coverage of the entire grid and the different dynamics, but you don't need to compute too many different. And so the first order thing that you would want to like to know is how much profit can you make as a developer in those different nodes. And so we here every scatter plot is one location. So it's kind of like, imagine you sit there in 2018 and you're trying to think like, where do I want to install my battery? And you just build one everywhere. And here's the mean annual profit. And what I think is already, at least to me, surprising is how large the profit deviation is. It's sort of like a fourfold, this is based on real-time market prices, sort of a fourfold difference. And the reason why it's so high, maybe counterintuitively, is because you have this fixed degradation cost in all locations. So even making a little bit more revenue gives you sort of an outsized change in profit. And the other thing that I want to draw your attention, this is the standard deviation of annual profit. So you're doing this for 6 years, 2019 to 2024, and you have a sort of, no matter what level of revenue you have, you always have substantial variation in here. And then even for the same level of profit, you could have varying amounts of volatility.
Verify, maybe set this for this day ahead or real time.
This is real time. I'll show you in a, we can get to there we go. This is both. So the red ones are the real time market prices. If you're acting on this alone, if you do day ahead market, I mean, we're not the first people to show it. I mean, there's multiple papers who show that if you act on the as a storage developer on the day ahead market prices, you're going to get less profit simply because there's less volatility in there. So all things equal, and you could imagine the reason in a second. The reason why I'm saying I think in reality you're probably somewhere in between is kind of twofold. On the one hand, you probably have a more sophisticated algorithm than just using day ahead prices. You're not going to like optimally respond to all the real time prices. And then you could, of course, as a developer, also split up your capacity where with like 50% you trade on one to get some locked in profit, and then with 50% you do something else. The key point I want to point out is that even amongst those high profit nodes, if you look at the sort of top 5% of nodes, like I don't want to be anywhere in PJM, I want to be at the profitable nodes. Year on year, 3/4 of them drop out. And that was actually the starting point we had. We went to some battery developers in Texas, and they were super happy that they found this like spot in Western Texas where they're making a lot of money. And then 2 years later, they weren't so happy anymore. They're like, what can we do so we can sort of figure out some of those issues? But you had a question.
Is this with perfect foresight of the prices, or you use some sort of forecast for the prices?
Yeah, no. So to the previous sort of like dynamic program, it's with assuming you know the vector for the next 24 days. 24 hours for a day. Yes. And again, I think the reality is going to be somewhere in between the red and the blue dots. But I think the key thing to keep in mind, 3/4 of locations drop out from looking great 1 year to the other. So depending on, especially from a developer perspective, it's sort of a winner's curse kind of situation. Like you think you have found a good location, you go there, and then the profit disappears. But we wanted to decompose this because so far this is just like overall profit that you're making. But the profit, of course, is sort of two components. And we're going to decompose the locational marginal price that you're responding to into the energy component and the congestion price. And there's a little disclaimer here. The congestion is going to include marginal losses. But basically what we're doing is, and conceptually, the energy price is the buy low, sell high. Like this is kind of, in my mind, the market choice. I can choose as a developer to go to PJM. I can choose to go to Texas. Like what is the fluctuation in a given market like? And then the congestion price is sort of like, what's the local effect of being in this one location? If you're particularly congested, like you might want to operate there. So you're kind of decomposing the two components.
Why is the volatility in the real-time market seems to be higher than or am I reading the plot?
No, you're reading it correctly. So I think it's twofold. It's the volatility of prices already in the real-time market is higher than in the day-ahead market in general. And then when it comes to profit, it's always profit is like revenue minus cost, because the cost is the same for all of those. Any little bit of extra volatility you get in the real-time market has an outsized effect on your profit. And so you're making overall less money, but you're reading this exactly right, where the profit on the real-time market is more volatile as well. And so maybe we keep in mind that like 3/4 of locations don't look that great the next year. And so if you're decomposing now this locational marginal price, we're going to call it energy contribution and congestion contribution. So basically, imagine you're operating the battery at a location for whatever is sort of profit optimal. And then you're going to look at, of the money I make is the black bars here. How much of this came from different energy prices throughout the day, and how much came from the congestion piece? And if you didn't choose your battery location carefully at all, say the median node, you're making, this is ranked by profit. You're not making that much money, but in particular, you're actually actively worsening congestion on the grid. So if we say like negative congestion contribution, this means like you're buying when congestion prices are already high and you're selling when congestion prices are low. And then what is happening as you kind of choose your like better and better locations, the energy contribution itself actually stays a little bit flat. And that makes sense, like the market, like there's a little bit of fluctuation across the day, but overall the energy should be fairly similar across most of the, across the entire market. The only reason why they're differing is at the different locations, you might operate your battery slightly differently. Like maybe at this node, you discharge at different hours than at the median node. But the thing that I found, at least to me, was surprising. If you look at those most profitable nodes, they get at the 99th percentile, for example, they get over 70% of their profit from just congestion behavior. And so I started the talk saying like, it's actually like if you have the sort of duck curve, you want to buy when the prices are low and then you want to sell when the prices are high. But that's true for all of those. But then if you look at what is actually driving the storage profit, at least across the like 6 years in PJM, it's actually how well can you capture congestion. And for in a second, I think what is interesting from a developer perspective, you have this weird tension where on the one hand, the same holds true, the sort of how quick those opportunities disappear. Like in the top 100 congested nodes, like half of them are not going to be around there next year. But on the other hand, you do want some congestion to sort of help you boost the profit. And so I think from a developer perspective, it's sort of where do I want to be where there is enough congestion so it boosts my profit, but not so much that the RTO or the central transmission planner is going to come and fix something about the node that I'm in. We're going to go in sequence. Yes.
I'm sorry, clarification. What is median and mean with respect to what?
Median and mean with respect to profit of the 576 nodes that we had across all 6 years. Yes.
If we talk about decisions that affect like years ahead, we know that congestion in the future is becoming more and more, like less predictable and not systematic because of renewables. So, this can change. I mean, like easily, like down the road. Are you going to discuss about this, or it's like a static? It's something that you have.
Yeah. I was going to see if this was an assertion or a question. Yeah. So 100%. Like I think if you or I had a perfect answer of like where's congestion going to be in 10 years from now, we wouldn't sit here. We would build batteries out there. Exactly. Fully agree. I think I'm not saying based on this like go and build in this location. I think the picture of at least two things to quantify is like how much actually congestion helps you in PJM and getting sort of a sense for it. And then even though you don't know where the congestion is going, I think you want to avoid the super high congested areas, because my sense would be that this is where actually someone else is going to take and step in with either more generation or some transmission line. I think where your question is going, though, is sort of like there's long-term uncertainty. And then the battery developer answer, I think, to this is like none of us knows like what is happening in 10 years from now. If I'm looking at my discounted cash flow, I really care about getting the next like 3 years or something right. So I think this is not saying like we can tell you exactly where to go. I think it's mostly figure out what is the right amount of congestion sort of arbitrage that you can take with you.
And it just a quick follow-up. It's related to what you mentioned very early that things can change if more batteries installed. I mean, like all this disappears. So like price will be like smoother and all this revenues. I mean, like you will fall. I mean, like to other.
Yes. So I think maybe the spirit of the talk is not one where like we'll leave here and be like out of those 576 nodes, this is the one to take. No. I think the spirit of the talk is more like things to be aware of and then helping us quantify sort of the effect size of some of those. But I like where your mind is going with like other batteries are going to come along, because that's exactly what we're going to talk about next. Yes.
So the data, so PJM reports the energy and congestion components.
Yeah, they report them separately. Okay. Yeah. Like they all get lumped up into the location marginal price. Well, actually, I don't know now because currently like things are changing with like data miner tool, but at least back to 2024, you could get them separately. Yes.
How do you decide where you locate like 165 nodes?
Currently, we don't. This is like an analysis, like pretend you had located one battery at each of the nodes, sort of a price-taking battery, sort of small battery. Like how would it like? So far, we're in a thought exercise realm. The next one, we're going to be in the real realm of actual batteries being installed. Yes.
Yeah, just want to ask you from the social good perspective, you don't want the congestion course to happen in that node. You want a perfect network, right? Although it couldn't happen.
Directionally, you want some network improvement until the cost of improving the network is going to be more than like the benefits you get from it. I'm not sure if you want to go all the way to a perfect network. Yeah.
But the congestion part is not good for the networks.
Well, this is terrible for the network. This, I would argue, is actually helpful. Like here, the battery is helpful. Like I think that basically the trade-off you have is like you have congestion in your network. You're not going to have sort of a copper plate kind of setup. Here, the battery at least is actively helping you relieve the congestion. But you're right, like maybe this level of congestion, maybe you don't want one battery developer making all this profit if it's hurting sort of everyone else in the network. Maybe the solution to this level of profit is actually building or upgrading the transmission line. And I think that's kind of the sweet spot where the developers want to figure out where do I want to be. Maybe this is the level of congestion that is sort of sustainable in the long run, where no one is going to come build a transmission line because of it, but I get some excess profit.
Thank you.
All right. Now we want to look at competition. So this one thing is just like things are changing and it's really hard to predict which node is going to be profitable. And beyond the point of it being hard in general, even if you were to get lucky and be in a really profitable node and the node stays profitable, that doesn't prevent anyone else from like coming to your location and build a battery as well. And anecdotally, this has been kind of the story that played out, but we wanted to see how large is this effect really. And so to do that, we go to EIA Form 860, where you can get the installation data of utility scale batteries. You get their capacity, their location, sort of like a geolocation. And we then went to Grid Status, which is like a data provider. It's cool if you don't already know it. Highly recommend you check it out, because what you can do with Grid Status, you can like on a map go to exactly the geolocation where the battery storage is and find the closest node. Because oftentimes when you download the node from the RTOs, they don't give you any location information. So this way, we know exactly where the batteries are and where the loads are. And we're getting the grid data from the Department of, actually don't know which government department is. We have the transmission infrastructure data. The data set now doesn't exist anymore because of the current administration that used to 2024 round. And so we're taking the 29 installations in KAISO and 19 installations in PJM of like actual battery installations. And so we get 48 combined. And they range kind of from 10 megawatts to like 350. We wanted at least 10 megawatts because our thought was for a battery to actually impact prices. If I look at like 1 megawatt or something really, really small, it's going to be harder to capture those kind of effects. And they're installed all the way from 2011, at least the grid status data goes back that far to 2023. So now we get to the point of like, what is the network effect and like, how do we capture this? So what we want to figure out is how much does one battery adjoining a node change the profitability of this node. And so the way we're doing it is...
do they require permission to be clear to join the battery operators?
Depends a bit on the size of the battery, but at some point in the site, you can go through the interconnection queue, yes.
So when the interconnection queue is clear, it must account for the existing batteries which are connected to the load, to the grid, right? At that node.
Account for the flexibility of it or like the approval process?
If I'm a new provider joining a node,
yes,
then the permission that I get depends on how many existing batteries are already on that node.
Yes. Although I think batteries, like my sense would be that just if you wanted to build a battery at a node that wasn't profitable, I don't think the system operator would stop you from it.
Yeah, but we are looking at the nodes where things can get worse, right? I mean, there are already some providers who are already installed, right? So I may be prevented from joining that node.
You're not legally prevented. It might just be a bad outcome. Yes. And I mean, at least I think the struggle with relying too much on the interconnection queue data is, I mean, it takes like X years, and then there's like different stages at which the projects could drop out. And so what you currently see is that there's different developers who are just going to commit like 10 different projects in different interconnection queues, and then exactly decide which one to drop. So it's kind of, I agree that there might be some information value in there, but it's like hard to evaluate. But for now, we're just trying to figure out like what is the value, like how does the battery joining reduce the profitability of a given node? And we're going to do it with a stack difference approach, and I have a little model to show how we're doing it. And then I'm curious to hear what you think about it. And I'm looking at time, so I might speed up a little after. But imagine you have a transmission line here, so we get that from the government agency, and then a battery were to join this node, and then you have different prices as well in other nodes. What we're going to do is we're going to take the node of the battery itself as our treatment node. That's where like the prices are going to change. And then we're going to take this main transmission line and we're going to go as close to the local demand center, like city, as we can before going into the demand center, and take this as the control node. And the idea is the following. Yes, they're in a network, so they're kind of related. The hope is that if they're on the same transmission line, they're sort of generally exposed to the same like network effects or particular patterns in this area. So like all of this could be in Western Texas, or I guess we're in CAISO, so all of this could be in San Diego. But then the local effect of the battery should be stronger here compared to there.
Why linear?
Why linear?
Why bother about a linear transmission? Close.
Because we're scared of Kirchhoff laws, or yeah, we basically wanted something that like is clearly relatable on the network, because we didn't want to ignore the network feature of it, but we didn't want to have to go through the trouble of like recomputing the entire effect. What would you do?
So I'm trying to ask a curious question. If there's a triangle network, or like like a triangle, right? I mean, still there is a blue node and a red node, right? I mean, what is there in your DID that actually requires you to have linear network?
No, we just wanted a control node and a, like, for us, clearly identifiable like treatment node and a control node. Like I'm asking what changed.
But why should they be on a linear network? That's what I'm asking.
No, they should be on the same network. Like we basically wanted it geographically in the same area, assuming that
there could be a network, right?
Yes.
And it could be a geographically close, but it doesn't have to be linearly, right? I mean, what you're saying is that there's a walk or there's a path on a network. A general network, I can have a general transmission network.
Yes.
And I can have a shortest walk or a path between the red node and the blue node. And I can...
No, they have to be on a transmission line. I mean, the electrons have to flow somehow, right?
Yeah.
Like maybe I'm not getting the question.
Yeah.
I think he says that it could be like a meshed
network.
like connecting like different
Where they could
nodes,
be
but
moved.
that's fine.
Yeah.
It would work. I mean, like,
Yeah. So
Okay, see, this is, I'm excited to talk to the engineers. Mesh network.
we are not just engineers. We are also
Engineers and more that know, well, people who know more about network architecture. Okay, so you wanted a mesh network. How would this be different?
that's what I'm saying, that it may not be different.
yeah,
I
probably
don't think it would be different.
it can work.
Yeah. So what I'm trying to say is that if it were a mesh network, it could still work.
Oh, yeah. So you're saying what I want is some geospatial proximity, but I don't need to enforce it.
Yeah.
Okay. Took a while, but we got there. Okay. Fully, yeah. So I think the main reason why we wanted it is we wanted to have sort of a reproducible way of like how to identify those two nodes. If I'm explaining to someone else, like out of all the nodes to choose from, like how do I identify my control? And this was a pretty like follow those rules and you'll find the control node. But yeah, what we want is we want proximity, so they're affected by the same market, and we want one to be less affected by the battery storage than the other. Okay. Cool. I mean, this is the worst part of the talk. So from here, it's all downhill. And we call those two things a cohort. So it's like treatment and control. And so what we're going to look at empirical specification is we're going to look at the profit in one location on one day in a given cohort. We're going to throw in some more amount fixed effects. Treatment, post treatment is basically is this where the location the battery is going to be installed. Post is are we in a month after which the battery was installed, and then this slightly convoluted expression here is actually pretty straightforward. We have 48 installations that happen at different points in time in different parts of the grid, and so we have those 48 cohorts. And for those profit opportunities, what we're basically saying is like, for a given battery that was installed somewhere, was this battery installed at this node on this point of time? And so what this psi-v ultimately calculates is only the effects of this one battery and its own kind of node. The z is an indicator of what you installed at that location at that day in this cohort. And so for every battery, we're going to get an estimate of how much did this battery at this node change the daily profit. And so you get, because we have 48 batteries, you're going to get 48 psi Bs, and then we're just going to average over this. And so the effect we're calculating is because we have the capacity, so we're estimating an effect per megawatt of storage that joins. So the 10 megawatt battery that joins, and this we're assuming is linear. I understand that not all capacity effects are linear in price, but the hope is that the batteries are small enough where it's approximately linear. And so across all 48 cohorts, we're going to calculate on average, how much does the battery, 1 megawatt of battery reduce the profitability at that node?
Why do we have the third term, gamma to post?
Gamma to post here.
Yeah.
Just to absorb, I guess we have the month fixed effects. It's at a cohort level. Like if there were any kind of local effect here that happened after the adoption for whatever reason, but it was the same across those two, then that would be absorbed. Like we really just care about the differential effect of the battery here locally.
Why is it additive in this way? So you're saying all the 48 are actually added in this way?
I'm saying the ZISD indicator is one where only this effect is only going to be one for the battery at this particular node. And so it's basically a way of being able to write this full equation for all 48 cohorts, but this effect is only going to be active and calculated for the given pair, but you can throw all of the pairs into the same equation. Yep. Okay, so we've done all the hard work. Now we can finally look at like what is the estimate, and the estimate is going to be 29 cents per megawatt hour per day. I know you might think this is a little bit disappointing with, well, why are we talking about 29 cents? We'll get there. I'm showing you two things. In the paper, we also do like congestion contribution today. I just want to focus on profit. One is a binary indicator. So if you don't account for the size at all, you get $6 per day. But I want to talk about the per megawatt effect. So 1 megawatt of battery joining reduces the profitability of a megawatt of battery existing by 29 cents per day. The 29 cents is usually not something to get overly excited about. How do I make this a little bit more appealing? Well, first of all, two things to note. There's 365 days in a year, and the average battery joining is 75 megawatts. So if you multiply this 29 cents by those two factors, you get to $7,820. So actually, the average battery joining in a given year reduces your profit per megawatt by $7,820. And we're not done yet, because if you're the battery developer that exists at this node, like let's say you own a battery there already and this new battery comes, this is per megawatt, and you might not just have one battery. In fact, the old batteries before, the batteries that were installed before the data that we gathered, their median size was 20 megawatts. So if you add the 20 megawatts, you get to 156. The point I'm trying to make is 29 cents per megawatt sounds pretty slow, but it's sort of a multiplicative effect. It's per megawatt of capacity joining on the megawatt of capacity existing. Mm-hmm. And so because both of those can be fairly large, and increasingly like the newer batteries are like 100, 200 megawatts, the effects end up actually scaling a fair bit. Like maybe I should pivot the story and not talk about 29 cents at all, but you get to $159,000 of sort of the average pair, average battery joining on average existing capacity. And if you just want to care about percentages, it's 12.4%.
So this is like on average, not
Yes.
for one specific location.
This is the average effect across all 48 locations. Yes. In the what we're estimating it for 4 months pre and post. So like there's the installation month, and then we look at 4 months pre and post to the point of like the grid is like there's many more things happening. We wanted a long enough period to like identify the effects, but not too long where like other things might be impacted.
So this is a very good analysis. Thank you. But the number could vary if, let's say, if I have some capacity of battery there, and if I have 1,000 more units of battery, right? So you said for existing per megawatt, right? So
Yes.
the megawatt hour. So, but depends on how big is the existing battery installation, right? I mean, this number could actually vary based on the initial amount which is already there.
Well, so
Why
currently
is
this
it
is like
linear,
per
right?
megawatt. So it's
Yeah.
like per megawatt existing for a megawatt joining.
Right.
That's why we have those sort of like.
But why do we have per
multiplications.
megawatt existing? Because in reality, they could be having there could be different result based on, let's say, 1 megawatt existing versus 100 megawatt existing.
Yeah, fair. I guess this one, well, to be fair, this one initially is just estimated on per megawatt joining.
Yeah.
And so that's why how you get to like the profit is going to be reduced for any megawatt that exists by 7,820 per year.
Yeah.
I guess this is a little bit of a leap of faith of
Yeah.
saying like on average we have 20 megawatts here, but to your point, it could be like 100 or it could be like any other amount.
Yeah.
I think the reason why I'm making this connection is this is sort of what is the price effect per megawatt. But if you're thinking like a developer, like, hey, I put this installation down and I paid X for it. If that installation happens to be 20 megawatt or 100, then this is going to be your loss, or like you reduce the profit. I don't want to call it a loss, your reduction in profit for the entire installation. I was told by multiple people in advance that you were inquisitive groups. I'm happy. I might, if you see me skip through like 1 or 2 slides on our mobile storage, I'll end us at no problem. But I'm happy to hear. So please keep going. Now, we've talked about very volatile congestion effects. We've talked about this competition estimate where choose whatever metric resonates the most with you, but maybe the 12.4%, like 12% of your profit on average is going to be going to disappear by a different battery joining. Of course, the grid might make new profit opportunities in the future, but that's the competition effect. Now, let's talk about business model innovation. There are many things about this. But one thing that I think is kind of intriguing is this particular picture, where so far we think about infrastructure as like, I commit, I'm going to be in this place for the next 15 years. Let's hope things work out for me. Well, some people like Nomad and there's a couple other companies as well have thought, well, this isn't good enough. Let's slap that battery on a flatbed and move it to wherever profit is highest. And what I think is kind of interesting, it's sort of on and what we want to talk about in the paper, of course, is like, can this profitably work? And where this comes from originally is actually disaster relief. Like this idea of putting a battery on a truck and driving it somewhere where power is needed isn't new. But if in disaster relief, let's say out in the Cape, the power goes down, you have huge willingness to pay from anyone to just bring any amount of power back. So in this disaster relief setting, clearly it's something that the utilities are interested in. What Nomad and a couple of other providers are trying to figure out, can I do this at a larger scale? And because there's some a misunderstanding when I talked to a colleague of this, I'm not talking about charging a battery. Like in a disaster relief setting, what is different is like you're charging a battery and then you're driving it with the full power somewhere and you discharge it here. That's not what I'm proposing. I guess what I'm proposing is like, because there's volatility in the grid, you're going to, for a couple of days or a couple of months, and I'll show you in a second how we're operationalizing this in a paper, operate your battery in one location. And then if the grid changes or there's more power supply at that node, you can take the same battery, move it on the truck to somewhere else. So rather than being locked in for 15 years, you can kind of move the battery around to wherever it's necessary.
What is it about battery? It could be any other DR, it could be, for example, a diesel generator, which is movable, right?
Yeah. No, there's nothing specific about the battery. I think it's a little better than a diesel generator because you don't need fuel supply. Like you can just do buying and selling. And if you could build very scalable solar power, let's say, that might also work. Although a lot of times the congestion is not in the purely supply side, but it's really in this timing mismatch. Yeah, there's nothing. Other ways could work similarly, but in general, I'm not aware of like many mobile infrastructure pieces yet. So that's why I'm excited about
Except from
the idea.
electric vehicles.
Electric vehicle.
Yes, precisely. Well, and
It says mobile storage as well.
exactly. No, and I think I had a conversation about this with I mentioned the project with BMW. I think this, like the electric vehicles, are going to take care of most of this congestion ultimately in sort of urban spaces. But I don't think you can convince like 100 people in Texas to drive like 3 hours into the desert to like stand there with their like the vehicles for 6 hours to like help decongest the grid. But this might be one way of addressing it. So I'm not saying this is like the only way, but it could sort of be compromised in different locations. Now,
Thinking about, sorry,
yeah.
practicality of this. So, we talked about interconnection So
Yes.
you would have to be able to plug and play,
Yeah.
basically.
I mean, this is in my mind, based on our conversation, there's two main obstacles to it. There's the engineering, like plug and play piece, where the way they're currently thinking about it is it's sort of let me prepare a certain node for like this kind of service, and this might have some like upfront cost, but then once it's like suitably prepared, I could connect some number of batteries, as many like up to a limit as I want, and then I might have, I don't know, 100 nodes in a system that are prepared like this, and I could move my fleet around. The bigger issue actually for them, this one they're pretty confident I think they can solve. The bigger issue right now is that in a lot of grids, there is regulation against used infrastructure, like used capacity or used items to be connected to the grid. So if you build it from scratch, you get interconnected, but you can't just take something off the scrap pile and connect it. Of course, this would be a very different application. That's where the idea of the law and the quality collide. So basically, imagine you have a truck. This is the most profitable location. This is just what I've just been explaining in the graph. This location is $100 a megawatt hour. You're kind of happy here. 30 days later, or some number of days later, it doesn't matter. The grid has kind of changed when you realize location B is better. You're going to drive out there. Now, what we're going to do is it's going to be this sort of repeated, like observed and optimized kind of loop where the truck is going to compare like where are the future arbitrage opportunities. Do I want to relocate? And we get to like whether you want and how much it might cost you. And then if you want to relocate, let's say there's some minimum length of stay that you need to be there. And this is because you're probably not, for like multiple reasons, operationally, you're not going to just have a truck driver sit there the entire time, like next to the battery to wait when it's their time. But also like there might be, again, from the regulatory perspective, there might be limits of you can't just plug and play every 2 hours.
You did an autonomous vehicle.
Hmm?
You did an autonomous vehicle.
And you'll see we make this number fairly short, but like depending on who you believe, like this is either this happens every few years, but this happens like every 7 days. And then once your minimum length of stay is exceeded, you go back to forecasting, you compare, do I want to move and do I want to relocate? Now, of course, without relocation cost, this would be purely better. Like, yeah, a flexible battery compared to a stationary battery, like why is there a comparison? What we wanted to figure out, like sort of how much better and how does this sort of moving cost make a difference? So our bottom-up estimate was about $1,000 for like one move. This is not with the preparation of the location, but that's just moving a truck. I think we're estimating on average 600 kilometers, having some labor there to do it. The actually trickier piece is that you also do have some opportunity costs. Like, so we're basically assuming whenever you move, you're going to lose an entire day of storage operations. But I'm going to show you at least one graph where we're varying this cost, and I'm going to show you like at what point in time does this stop being a valuable business model.
The lever has to stay there to protect the batteries, no? I mean, somebody has to stay there or is just abandoned once it's connected.
Abandoned is not the word I would choose. Left there happily working by itself. Yeah, no. This is, but your point is well taken. Like, if you think that this requires a lot of, let's say, security cost,
yeah,
and you want to maybe not even as a one-time cost, like a sort of continuous thing, then maybe this business model is completely done. Like, I would be somewhat hopeful that this works. I would be somewhat bullish, but this is where I'm not saying it's going to work. I'm going to show you under which circumstances it does work. I'm going to skip the math, but basically what we're doing is we're going to find the best location to move to, and we're going to forecast future profit based on some exponential smoothing forecast of like what the future price is going to be. And then we're going to assume all prices on average are going to be like this exponential smoothing. You could certainly do more sophisticated forecasts, and we have some other methods in the techniques as well. And we're telling basically operators how to like do those forecasts optimally. Now, how often would you move? I think this goes to this question of like, does this feasibly work? Or if you do this in PJM for 6 years, those are sort of the best locations that repeatedly trucks go to. So we're doing this now at a sort of smaller scale. A truck is 1 megawatt of power, 2 megawatt hours. And so it kind of keeps repeating the same locations, but also in 6 years, it only moves, I think, like 16 times. Yeah, we start at 0, we go to 15. Mm-hmm. So it's not super frequent. And even if you let it move every 7 days, it's often not profitable to move. So it's kind of like you're moving every 30 to 90 days kind of opportunity right now. And And now the big drum roll, how much more profit do you make? Maybe I should like hide this bar. The trouble is like, what is your comparison? So like the movable battery can always make use of some kind of profit. And we've seen beforehand that different nodes have very different profit from a stationary perspective. So we're comparing here against the median of the top 10 most profitable locations, which is already a pretty good benchmark. And then at $1,000 moving cost, the mobile battery outperforms it by 11, 17, and so on %. If you're comparing against not the top 10, this difference is going to blow up. If you just compare against the average profited storage installation, this is like 100% or so better. So the profit opportunity is kind of there. And now to a point of how long could I do it for? Depends on what you're assuming on moving costs. And now on the we have on the x-axis the moving cost in sort of log scale. And then are you using real-time prices and day-ahead prices again as blue and red? And so this is kind of a profitable opportunity up until about $8,000 or so of moving cost. And so I think this is kind of then the business challenge of like, can we make this, for example, with autonomous vehicles with like plug and play authorization from the RTO, and can we make this work? In the appendix, we also show like what's the sort of social benefit of this, because of course, if you can reduce the congestion, you're lowering the prices for everyone. So this is actually one of those stories where the developer makes a lot of money, but it's actually beneficial for the grid as well. So the hope is that ultimately there might be some willingness to change regulation accordingly to allow this more easily. And then the final piece that we do is we kind of combine all the things that we've done. And I know I'm getting close on time, but I want to show you this as a sort of final thing, which is we have this competition effect. We know like a battery joining is going to do something to prices. And we have our baseline arbitrage profits. Now imagine you add one MESS unit, so one truck driving around through the grid, and you put it at the most profitable location and let it do its most profitable thing. Then you apply the impact of competition of this one truck on the price, which is going to be kind of small initially. And then you either stop if there's no more profitable truck to be added, or you keep adding trucks to this fleet that are moving around through PJM, which is kind of our idea of like figuring out how large is this as an opportunity. It's just like 4 trucks that are going to be driving around to 4,000. So maybe you can like think in your head, like what number do you think, how many trucks of 1 megawatt and 2 megawatt hours each could PJM accommodate profitably?
3.
Okay, almost 7,500.
So close.
Yes, but we have a 3 somewhere on this graph. Actually, no, we have eliminated financial scheme. No, but so whether you believe the numbers, again, this is like, we can play around with different estimates as well, but it's about 7.5 gigawatts of battery capacity that would be profitable to have drive around. And so this would be 7,500 mobile trucks. And yeah, if you do day-ahead market profit, of course, again, there's less opportunity, but even with day-ahead market prices, which is actually the thing you can lock in, it would be 5 gigawatts. Of course, there's still the engineering challenges we talked about, but there would be very little pricing risk. And so with that, thank you very much for listening. It's, I hope, 2 sort of things to think about: volatility and congestion risk and how much it's changing, getting a good quantifier on it. And then this competition risk, 29 cents per megawatt hour or 156,000, depending on what you prefer. And hopefully kind of an avenue towards getting flexible energy infrastructure. Thank you.
Interesting. So what do you assume like perfect information so you find the best possible locations?
No, so here we're in the we're assuming this exponential smoothing forecast. So what we're doing is that we do this exponential smoothing forecast of your design, and you based on the product prices, you optimize the smoothing parameters. So your forecast is like reasonable good, but it's still somewhat inaccurate. And then you relocate based on that to predict